Okay, so today we are going to build a variational autoencoder using MNIST as the dataset, the simplest data possible, and using stacked linear layers in the encoder and the decoder. So just a very simple autoencoder, and we are going to show the reconstructions, show some samples, some built reconstructions from a prior, and then I think that'll be it for today's video. Well, for the first video, and then I think I'll try to record scaling, so moving up the dataset and complexity to CFR10 and showing how the network performs, and then I'll have to add some convolutional layers to adjust for the additional complexity. I think I'll keep the VAE time boxed, scoped to that, and I'll move on to clip after. I don't want to spend too much time on this. I already sort of spent quite a bit of time toying around with this on my own, but so yeah, I think I have some other things I'd like to show, but I think that'll be in the next video. So I'm pretty sure that's it for this. Pretty straightforward. So let's get started. So okay. So I'm not, okay, so I have code to, so what I'm going to implement is the training loop, the training and validation loop, and the actual model and the loss function. The rest, a lot of it is repeated code that I've used before, like matplotlib code to display images and getting the train and the validation loader, stuff like that. I only want to, so like, loading the config file. I only want to show code that I think is sort of really good to keep in your recent memory. So for that reason, I'm only going to show the training, the test loop, and the model that I'm building. The rest, I don't know, the rest is just scaffolding. I don't think it's too pertinent to understanding machine learning. So yeah, let's get started. So let's type out, okay, yeah. So we load so here's the main method. We load the config file, and then I'm gonna do a summary. I showed summary in the last video for UNet. Summary is a great way I like to build models, just to make sure the dimensions of the layers are aligned and that the model is actually dimensionally valid. And if it's not, the summary won't work, you'll get an error. So what we're going to do is just build the model and then continue to run summary and make sure that the output shape, or that the shape of the tensor we're sending through, makes sense. So let's start building the model. So okay, MLP, so variational encoder MLP. Inherits from NN module as always. Constructor. So here's the notes from the derivation. So remember, we're building this. We're building this right here. So it takes an image as an input. For the linear case, we're going to flatten the input because we're using linear layers. And then we're going to go from the input layer to the one hidden layer, and then to one linear layer for mu, one linear layer for sigma. Mu and sigma are both latent vectors of a dimensional size of our choosing. We're going to say 16. Then we're going to do the reparameterization trick. So we're going to we're going to create a vector where each index is a sample from a normal distribution, and it's going to be the size of mu and sigma. And then we're going to add those together. That'll give us our Z. And then we'll send Z through a decoder, which is stacked linear layers of increasing dimensions, all the way back to our output dimension, which is X hat. And then we're going to send X hat through our we're going to generate a reconstruction loss and a regularization loss according to this right here, this equation. And then we're going to backpropagate that loss to the network. So we need, back to our constructor, input dims, hidden dims, latent. So I think 28, so 784. So that's our flattened 28 by 28 MNIST image. Say 256, 16. Dot linear. Input hidden. Hidden latent. I'm calling this is log variance because you'll see the analytical form of KL divergence. So the analytical form of KL divergence requires log variance. It's just what the closed form solutions of the equations that we're using resolve to. It'll be more clear once I do KL divergence here. So C2. So now we're going to do the decoder. Okay. Recording, yes, we are recording. Forward. I'm going to put some placeholders here. So self.encoder x station. Reparameterize. Gives us z. And then x hat equals, this is going to give us this. So our encoder is going to put output mu and sigma. We pass this into reparameterize. That gives us our latent z. And then self dot. We send z through the decoder. And that gives us our reconstruction. We're going to return the reconstruction, mu, and z. So our encoder is going to be self.fc1. So we need to add nonlinearization. So just relu torch.lu mu log variance. So this, wait, we don't need nonlinearization. We just want to take the raw logits. So pretty sure that's that. Actually, so yeah, let's run summary. So, right, we're reading all our configuration variables, just as I showed in our other video. So here's a brief summary. You can pause the video just to get a quick look at what these are. And we're just it's gonna hit our main function, read the config variables, and then our model type is the MLP, so we're just gonna load this. All the parameters are default values. 16. Input shape is going to be a flattened, it's just a dummy variable, but it's a flat, it represents a flattened MNIST image. Yeah, and then we just check out the summary. Config summary, true, train model, false. Okay. Oh, right, it doesn't have these methods. Oh. Oh. Okay. 1 by 16, 1 by 16. Yeah, 2 1 by 16 layers. So standard deviation is going to be torch exponent. So we need, so this is log variance. Remember, it's log sigma squared. We need sigma, so we need to we raise this to a power of e. That cancels out the log, and then we do a square root, and that gives us sigma. We recover sigma that way. So that's what we're doing here. And then epsilon is we need to sample from a standard normal. So we just do torch rand n like. So rand n is just normal sampling, and then like is just to make sure it's the shape of whatever the tensor is we pass here. So this will be epsilon will be a tensor that matches the dimensional size of mu and standard deviation. And yeah, this gives us our z. So now our decoder, actually let's run this. Self. That works. So decoder. Self torch dot use self dot sc to z. FC 3x. Oh. So we're not going to send this last layer through tanh. It's not going to be probabilities. We're going to keep the raw logics because we're going to use binary cross entropy with logics. We're going to use the PyTorch function binary cross entropy with logics. Also, I need to mention, because we're doing MNIST data, we're not doing, which is not RGB, it's grayscale. We're actually gonna model this. We're gonna do like we're gonna make a modeling assumption that so if you remember in the derivation video, the modeling assumption was that the predictive distribution, the modeling assumption was that the predictive distribution is a multivariate Gaussian with mean x hat and variance sigma, right? So essentially, each pixel, the predictive distribution was going to be a product of PDFs for each pixel, where the PDF is of a univariate Gaussian with independent univariate Gaussians, right? So your whole entire picture would be, all of your pixels, which would be a multivariate Gaussian with a diagonal covariance matrix. So that means that your pixels, the dimensions of your Gaussian are independent. Another way you can look at that is a univariate Gaussian for each pixel, where each pixel is independent, and then you take the product of them. So when we were calculating the likelihood, we took the log of the product, right? Which becomes a sum of the log of a Gaussian, which when you do the math turns into the mean squared error loss here. Our modeling assumption this time, since it's MNIST data, which is grayscale, is we're instead of using a Gaussian PDF, we're going to use a Bernoulli PDF. So each pixel is a Bernoulli distribution, which is essentially, it's a 0 or a 1. So it's going to output a probability between 0 and 1 that determines the intensity of the pixel value, right? So you can see it's like an approximation of a grayscale. So it's not quite 0 or 1 because MNIST isn't black or white, it's grayscale. And the way we're modeling that is the probability represents the intensity of the pixel, of the pixel value. So each pixel will be represented by a Bernoulli, and the likelihood will be a product of all of the PDF for all of the Bernoulli distributions for each pixel. And when you take the log likelihood of that and you do some math, it ends up, like usual, being binary cross entropy. So it'll be a sum right. So it'll be a sum of binary cross entropy for each pixel value. And right, so that's what I'm going to do next. Let me run this. All right. So I'll do the loss next. All right, I mentioned that because I was talking about the logics that we're outputting, and that sort of ties into what the output, what the reconstruction looks like. And in the case of MNIST, it's going to be the pixels are going to be modeled with Bernoulli distributions. So let's save the loss function for now. Let's fill that in when we get to it. So let's do the training and the test loop. So dataset. Just a config variable pointing to the data that's already on my local drive. Transform. Transform t.compose. Just going to turn it into a tensor. I'm not going to resize the images, just keep them 28 by 28, which is their default size. I think just get train validation. So I'm running this method get, so it just returns the data loaders when I pass in the data set, splits it into training and validation. I've already done that multiple times in previous videos. Now, model. Let's make it explicit. Send it to the device, which is specified in the config. Optimizer. We don't need a fancy optimizer for this, but why not? We can use RMS prop and momentum. There's no reason not to use AtomW. Learning rate specified in the config file. We don't need criterion because we already specified our loss function. We're not using a default one. Well, we haven't specified it yet, but we have a placeholder. We're going to fill that in. I think we can start our training loop now. Let's just run it, see if it works. Turn this to true. Summary false. Don't need this anymore. Pretty sure we're getting what we want. Okay. With TQDM. Train data loader. So pass the training data loader to TQDM. So we have a nice loading bar because we are going to experiment it. Typically we experiment a lot with these models locally. So we need clean outputs to be able to parse our, just parse our results and make sure this is making sense. Training. So with as P bar, so it's going to be our progress bar for, so we'll put the model.train for inputs. Now this is a generation task, so our ground truth labels are going to be the actual data, so we don't actually need labels. We're going to use the inputs as labels. So in p bar, just run that. Model, so inputs to send it to the device, always config device model inputs. That's going to give us reconstruction or reconstructed images, mu, log variance. And then we optimize it, we zero out the gradients from the last run, from the last batch, and now we do loss. Okay. This is going to take in inputs, targets. So inputs are going to be the reconstruction. The targets are going to be the inputs, right? The targets are so the ground truth is actually the data, the original data point, and then mu, which is a tensor, log variance, which is a tensor. And now I'm actually, because I'm going to do two different types of variational autoencoders, I'm going to reuse this loss function, and I'm going to change the variational autoencoder I'm using for MNIST is going to be the variational autoencoder that for the MLP is going to be used for the MNIST data, which the loss function will be binary cross entropy. And for CFAR10, the loss function is going to be, we're modeling the predictive distribution with Gaussians. The loss function becomes the mean squared error. So I'm passing in the actual loss function as an argument here. So I don't have to, so I can reuse this function. So binary cross entropy with logics because I'm not using 10H. So okay, so let's go to loss now. Okay. So we need, okay, so what we need is reconstruction loss, KL divergence loss, and then the real loss, and then the loss is going to be, and we're going to return reconstruction loss plus the KL divergence loss as a mean. And then we're going to divide it by input dot size, so the size of the batch. Okay. So because the reconstruction loss is going to be the sum over all elements in the batch, the KL divergence loss is going to be a sum over all elements in the batch. We're going to add those two together, and we want a mean. So we divide by input dot size, right? So I'm calculating this here just as a mean because I just think it's cleaner doing it as a mean. I mean, well, right, this isn't, I mean, I guess the way I'm writing it here is not on the batch level. I'm doing it for an individual sample. But when we're doing it on the batch level, we need the loss as a mean. So, okay. For the reconstruction loss, okay, we have this analytical form of KL. Actually, wait, no, the reconstruction loss is binary cross entropy. I don't have it in this derivation because I did the derivation for RGB, Gaussian PDFs. But in the Bernoulli case, the likelihood simplifies to binary cross entropy. So I'm going to do the binary cross entropy loss on a pixel level for each, and I'm going to sum it across. I'm going to sum it across all images in the batch. So that's our loss, right? Functions, but I'm just going to put a placeholder here so I can remember what's passed in. So it's input, target, and then reduction. So the input, target, and then reduction. It's going to be sum, right? So we're going to calculate binary cross entropy loss on a pixel level per pixel for each image across all images in the batch. Sum that, and that'll give us our reconstruction loss. And then now the KL divergence is what I wanted to cover. Another thing I didn't cover explicitly in the derivation video, but here you go. This analytical form of KL divergence. So remember, KL divergence it's a measure of divergence between two distributions R and S, which is it's the expectation under R of the log of R divided by S. So in our case, it's the measure of divergence between our posterior distribution Q of Z of X, which is the distribution where we're pulling our Z's from, and it's the measure of divergence between Q of Z of X and an assumed prior P of Z, which in our case is going to be a standard normal. To get this closed form solution, you just plug the PDF. You plug the PDF for Q. So Q is going to be parameterized by X hat and sigma squared, which we will just call mu and sigma. And then Z is going to be parameterized by 0 in the identity matrix, right? It's just a standard normal. So when we plug those in for the PDFs of R and S, right, which is going to be Q and P, and then we simplify, you just do the math and we get this. And this is where log variance comes from, because this is the log variance variable that I'm referencing. We don't reference sigma squared. We reference log of sigma squared. One, because that's what the math resolves to, but it's just, and it just so happens that logs are much easier to look at when it comes to probabilities than anything else, because probabilities can tend to get really, really tiny. So, which can mess up your neural network. It can mess up the gradients. It can mess up the flow of gradients. So, okay, yeah, this is where log variance is coming from. This is why I call it log variance as an output from the encoder, and that's why we're working with log variance. So I'm basically just gonna write. This is our KL divergence term. I'm literally gonna write this out, and then it's gonna resolve to a number that we use in our loss. So 1 minus log variance minus mu wait, this is just log variance. Log variance is log sigma squared. Right, and then E raised to, so that's this equation right here. So I think this should work. No, this has to be torch.sum, otherwise it's not gonna return a tensor. It needs to know that it is a tensor operation. Mostly because we have this one here. If we just had these here, which are all tensors, it would automatically do a tensor operation. But I think because of this one, we actually need to put the torch.sum there to explicitly say, let PyTorch know that this is a tensor operation. What happens if we run this? So that's our loss. Loss dot backward. Optimizer. P-bar dot I didn't flatten the inputs. Yeah, I didn't flatten the inputs. It's expecting right. There shouldn't be any 28s in our data. Torch stuff, flatten. Start dim on the channel dimension. So we're going to flatten starting at the channel dimension. Total train loss plus equals loss dot item. Set postfix. So we're going to update the progress bar. Train loss equals. Oh, just call it loss. Okay. So now we're going to calculate the average loss or the average loss per batch, which is we're just going to take the accumulated training loss divided by the size of the training data. Let's run that. I think this looks right, actually. Oh, I think this is right. The reason why you're seeing such large loss values is because we are summing over. So let's just look at the reconstruction loss, for instance, right? We're summing over, we're computing binary cross entropy for each pixel in an image across all pixels, across all images in that batch, right? So we're starting off with, our model is starting off with random values. So, I mean, we could do some math and figure out exactly what an approximated starting loss would be, but, you know, just thinking about it, you know, because we're doing it on a pixel level, we're gonna, you know, we're gonna get quite a bit of loss, and that's just the reconstruction term. So just make sure this is right. Should be plus. Huh. I knew something was off. I was like, these values are just a little bit too big. Yeah, this should be plus. I knew something was off. Okay. Train, I'm gonna replace. Okay. I'm gonna remove. Remove that. Model.eval. For that. This looks good so far. The validation is lower than the training loss, but they're both, it seems like they're both tracking down, which is okay. So now we're going to show reconstructions. Oh. Show samples, interpolate latents. Oh. Interpolate latents, config, model, dataset, num steps, 10. Show samples, config, model, latent dance, 16, I'm going to use 8. So yeah, let's run this for maybe 10 epochs. Actually, let's make sure that these work. So let's run this for an epoch, 2 epochs, and see what we get. So we're gonna run training and validation 2 times, and then we're gonna show some reconstructions, show some samples from the latent dimension, and then we're gonna do some interpolation between latent values. Yeah, so it looks like it's, so the top are the originals and the bottom are the reconstructions. So after 2 epochs, this looks pretty decent. Decode. Oh, decoder. Decode. Encode. I'm gonna, I want to divide this by, yeah, this looks pretty good. So latent interpolation basically draws a sample from the prior, which maps to a certain digit. It'll map to a closest digit, and then you basically take 2 latents and then you interpolate between the numbers that they represent. So you take 2 latents that are close in space and you interpolate between the numbers that they represent and just show those reconstructions. Send them to the decoder and show those reconstructions. So you can see the code. I'm not covering that. You all know that I hate matplotlib, so I appreciate the matplotlib gods. Thank you so much for your diligent effort in bringing such an amazing framework. I still hate it with passion. What can I say? All right, so this looks good. So this train loss, I want to show the average loss thus far. This is just showing the sum. So I'm gonna divide this by the number of batches thus far. So batch index. I think that should give us what we want. It might not be perfect. It should be a good approximation. It should be, yeah, it should be a pretty unbiased, relatively unbiased approximation. Division by 0. Oh, okay. Yeah. we'll do the same thing. Oh. Oh. All right. So while this is running, just to make sure that they're both nice and neat, printing nice values. So, okay, just a quick review. Yeah, that's nice. Much better. So, all right, we have our autoencoder, takes in an X, sends it through some stacked linear layers, outputs latent vector, outputs latent vectors mu and sigma. We reparameterize and send it through some stacked linear layers in the decoder. It's good. And it outputs our reconstructed image from which we calculate the loss, the reconstruction loss, and the regularization. We add them together. Remember, this is going to be, we're minimizing the sum here. We're not maximizing the difference, we're minimizing the sum, right? So over here, we can see we have our encoder and our decoder. We encode, reparameterize, decode, reparameterization. We have to recover we have to get the standard deviation. We recover sigma by exponentiating. And then we get the standard deviation by taking the square root. We sample from a normal distribution. Reparameterization trick. For the loss function, we're using binary cross entropy. That's what's this callable function here. And then we basically, for the predictive distribution in the case of MNIST data, which is grayscale, is going to model each image as an independent, each image as the likelihood. So the predictive distribution is going to be independent Bernoullis for each pixel. So the likelihood becomes a product of those Bernoullis. The log likelihood is the sum of the log of those Bernoullis, which when you reduce it becomes the binary cross entropy. So you're going to sum over the binary cross entropy value for each pixel across all pixels, across all images in that batch. You're going to add the reconstruction and the Kale divergence loss, divide by the size of the batch to get the average value. And then in your training loop, you're going to output that, you're going to back propagate on that loss value. And then we're showing the reconstructions. We're showing some samples from the prior, some reconstructed samples from the prior, and then we're showing how you can interpolate between latent vectors to just give you a sense of what these latent features mean. Yeah, so next we're going to scale up. We're going to use a data set of increasing complexity, and I'll have to use some stacked convolutional layers, some ResNet blocks to be able to get some decent reconstruction loss. So yeah, thanks for watching.